Okay, so welcome to this meeting, this lecture. My name is Gideon Bizenye. As usual, we will go through the procedure for conducting a hypothesis test, something we have seen before. However, this time we will move further to look not just into a single population, but rather we would look at how do you do your hypothesis test when you have two populations. First of all, this lecture is strictly based on chapters 9 and chapter 10 of the course textbook, which you can also find as an online book. So you're encouraged to actually read, especially chapter 9. Just to make sure that we are starting from the same point of departure. I do know that you might have been reading, but I will do some recall, just some key concepts from the one population case that we had discussed in our previous two lectures. I will talk a few words about t-test, and then we will focus on how to conduct the inference when you have two populations. So when we say two populations, it means that you have two groups that may or may not be independent from each other. We would end the lecture by discussing about chi-square, something that I think B asked a question about last time, and also a few words about ANOVA and MANOVA. As we move along, you would see the pattern. The pattern is that we are increasing the complexity, or at least we face increasing complexity as we deal with different dimensions of two or more populations. When I say increasing complexity, it's because maybe we want to study one group and the other, and we want to study more than one thing from one group and the other, and that's where all of these complexity comes from. I use this picture today just to give you an idea of some of the things that we'll talk about. Is there anybody who has seen this picture before, this graph here? If nobody has seen that, don't worry about it. This is a chi-square distribution. If you think of a distribution like we started talking about plotting a histogram, and then we talk a lot about the normal uniform distribution, which was the bell shape. Then you also have other kinds of distribution that, as we've seen also in the picture that I've been using in the previous lecture, that there can be different types of distributions. And this graph here is what we refer to as a chi-square, which we would also see during the lecture. Okay, so let's begin. We will recall that in our previous lectures, we tried to understand the concept of a hypothesis as it applies to a single population. A single population can be a single group or system that we want to study. It can be a group of people, or it can be a group of some artificial system. It can be a group of customers to a business. It can be a group of vehicles. It can be a group of books or whatever we are studying. When we just have one group, it's a single population, and that's what we've been talking about. So when we all along with hypothesis, the one very fundamental thing that we've been discussing is inference. And when we say inference, is we're trying to draw a conclusion from a claim using some kind of statistics about either the sample from the group or the population. And the sample, as we know, is just a subset. So that process which we use to make that inference about the population based on the sample. And we recall that we said the reason why we are interested in this is because often we do not have the complete information about the population. We can only sample the population. In other words, we can only select a subset of the entire system. And then collect data about that subset. But we are more interested in verifying whether something about that subset is also true about the population. How likely is it true about the population? Or how can we approximate what we learned from the sample to the population? And this often, with the idea of a hypothesis, often means that we have a claim, which is a basic statement, which we say is a basic fact about the group, and we want to see whether that claim is valid, or to what extent that claim is more likely to be true. And therefore we set an alternative hypothesis, which we say is also called the alpha hypothesis, or sometimes you can see H1, and we call the claim the null hypothesis. So the alternative hypothesis often contradicts the null hypothesis, and we want to prove either whether we can admit, you keep saying admit or reject the null hypothesis. And last time I remember there was a question whether we can apply the test on the alternative hypothesis. The fact that they are contradictory or mutually exclusive means that either one of them can hold, not the other. We often apply the test to the alternative, to the null, and if we can admit or reject the null, it automatically says something about the alternative. So we do not apply the test on the alternative. One thing that we have talked about in those previous lectures was about the fact that sometimes we could end up in a situation where we're making an error, not because we want it, but because we inadvertently might be mistaken. And therefore, we might run into a situation where we might reject the null. Sorry, that wasn't my intention there. We might run into a situation where we reject the null hypothesis when the case is that it should not have been rejected. So in that case, we are committing, or in that case, we made an error. And we call this the type 1 error. And we use alpha to represent the chances that we might be committing a type 1 error. We could also run into a situation where we reject the null hypothesis when it actually is, where we fail to reject the null hypothesis when it actually shouldn't be rejected. Basically, if the null hypothesis is rejected when it should be true, when it's, if we fail to reject the null hypothesis when it's actually supposed to be false, then we have a type 2 error, and we denote that with a beta. So the type 1 error is when we reject the null hypothesis, when we actually should not have rejected it, then it's a type 1 error. But if we fail to reject it when we actually should be rejecting it, then we commit a type 2 error. One other important thing that we also discussed was the idea of p-values. That means the probability that of obtaining the observed sample results, assuming that the null hypothesis is true. If the null hypothesis is true, what is the chances that the sample results can be obtained? And we quantify that chance using a statistic called p-value. In other words, to what extent can we approximate the statistic from the sample to the population, given that the null hypothesis is true? How close is this approximation? And therefore, we use this quantification or this statistic as an evidence. And the smaller that evidence was, then the chances got very small, and we could use a significance level or a threshold or a cutoff value as alpha to decide whether it was close enough or it's not close enough. And if it's close enough, depending on the cutoff value, then we would use that as a basis to either admit or reject the null hypothesis. The procedure for doing this for a single population, as we'll see, it remains the same for more than one population, for two populations. One other key thing that we have also talked about is the word or the concept or the idea of a distribution. And I keep saying it because it might be difficult to comprehend mentally what a distribution means. A distribution here being the idea that if you look at how the values of our original data spread, what kind of pattern do we see? So when we say the value spread is some form of in a very simple terms, a frequency where we say, okay, in this population, if the values are ranging between 5 and 10, for 5, how many points do we have? For 6, how many points do we have? For 7, how many points do we have? And then we plot those numbers and we see that all the population follows a certain distribution. The distribution can be described as maybe a uniform distribution, or maybe it follows a certain type of distribution. There are different names that are given to these depending on the shape and their properties. So when we are testing the hypothesis about the means of a population, different distributions are used depending on whether the population standard deviation is known or unknown. So this is very important for us to decide to use the correct statistics. So we need to be able to either verify that the population follows a certain distribution, or we need to be able to find other reasons in order for us to use a certain approximation. And I also mentioned the fact that sometimes we know we may not have data about the complete population, but maybe we have some other information about the population. Such information could be something like a standard deviation. We know the population standard deviation. It does affect the kind of approximation we can do. So we'll use the standard normal distribution if we know the population standard deviation. But if we do not know that, then that is where the T distribution comes in, or the student T test. A lot of the times I also said we would use the T distribution because we often may not, or we often do not know the standard deviation. In some cases we may, but a lot of times that's why many students who do a course like this, or in many questions, or in many studies that you see, you would see that they are using a T distribution. So in other words, the T distribution is mostly used compared to the Z. And the reason for that you should know is that because maybe it's hard to get the population standard deviation. We could study at least two statistics, looking at the sample or looking at the population. We could either want to study the population and sample means, basically the average value in the population and the average value in the sample. So the mean is the average value. Or we could study the proportions. The proportions in this case is how the different values or the ratios of the different values are distributed. A certain proportion of a certain answer or a certain value in the sample can be compared to the proportion of that value in the population. So when we are testing the hypothesis about the proportions, we use the normal distribution if we have a certain set of conditions that are met. And you really should study and understand what are these conditions which we have already seen. This will be useful for you if you want to conduct, say, a thesis, or even if you are in an exams and maybe a question is formulated and you are given certain information, you should be able to know that in this case, I should use a Z distribution, or I should use a student T distribution. And in the case of the proportions, if the statistic of interest is about proportions, then we have two choices. The second choice we haven't talked about is the binomial distribution, because we decided to end at the level of the Z distribution. And the idea is that you often would, at least for this course, tend to use or focus on the Z distribution, but you should also be aware that if the conditions are violated, then you should use you should ideally, at least conceptually, know that in that case you should use the binomial distribution. And you can also study the binomial distribution from the textbook that we are using. We haven't just gone into the details of that distribution during the lectures. So the choice of the distribution that you choose in order to approximate the sample proportions to your population proportions is dependent. Those conditions that we talk about here, they are dependent on the size of your sample. They are also dependent on whether we know or we do not know the standard deviation of the population. This idea, whether we know or we do not know the standard deviation of the population, it seems to be very useful, as you've seen, in whether we are using a certain distribution or not, particularly whether we are making assumptions about the normal distribution. One additional thing to keep in mind about these distributions is that there are two kinds that we are talking about. Either we know that the actual data itself has a normal distribution, and if we do not know that, which might often be the case, then we could also know that if we take different samples and record their mean, or take different samples and record values from the samples. So for sample 1, we know the mean, for sample 2, from the same population. And at the end, if we look at the distribution of those mean values, we see that they follow a normal distribution. So that's the second case. The first case is that the raw data itself in the sample, in the population, follows this distribution, or the statistics that we are calculating by repeatedly taking the samples follows a normal distribution. So if we know the first one, we don't need to verify the second. If we don't know the first, we then talk about the second. One also important thing that we talked about from our previous lecture was really the idea of how do you get p-values. Here, I think you maybe doesn't need a lot of focus on this. And the reason is that you often have this information given to you in some way. Given to you as in, even in practice when you're doing your thesis, you can have lookup tables, or you might just have some kind of a dictionary information in a program that will give you the p-value for a given level of alpha, or for a given level of for a given cut-off value. And we know that these p-values are integrals. Now, we don't want to go into too much mathematics here. Integrals is areas. We are looking at If I say, what is the area of a square? You can tell me it's one side. You take one side and you multiply that by 4. If I say, what is the area of a rectangle, of a triangle, you know that. But if you have a curve and I ask you, what is the area? There is a mathematical procedure for how to do that. And p-values are, in some sense, we are calculating the area of a part of a curve. For that calculation, you often are given those values, and you simply need to know the uh, the uh, the threshold or the cutoff. Where do I start from this axis going forward? Whether it is the uh, left tail or it is the right tail, and then you can look up the corresponding area. But it is important, however, to know whether you are dealing with a left tail area or a left tail calculation of the p-value, or you're dealing with the right tail, or you're dealing with both. In either case, when you have your p-value, you would use it in order to compare, and you are comparing it with, you use your p-value to compare it with your alpha, with your significance level, in order to be able to conclude or to come up with a statement of the likelihood that the statistic you're looking at for the sample is more closer or far away from the population. That's from the population statistic, from the corresponding value in the population. If you're talking about the mean, you want to ask whether this sample mean is very close to the population mean, or it is too far away from the population mean. The p-value in combination to the cutoff points that you are using helps you to be able to make a conclusion, an informed conclusion about that situation. So when the p-value is very small, then you can think that the observed value is unlikely. And mark the fact that I'm not doing a conclusive statement here. It is unlikely to have occurred by chance alone, and therefore it provides evidence against the null hypothesis. So it is a strong indicator that the null hypothesis uh, cannot be admitted because the p-value is very small. In order for us to determine how this p-value should be obtained, we need to determine the test statistic and its corresponding distribution. It is important that we know whether the test statistic refers to either we are looking at the mean or the proportions under certain conditions. The reason why we do that is because then we know what kind of distribution that we should follow. So the test statistics measures how far the sample estimate is from the hypothesis value under the null hypothesis. Using the test statistics, we calculate the approximate value of the, using the test statistic with the distribution, we calculate the approximate value of that quantity that we want to compare with the corresponding p-value for that distribution. So once we have the test statistic and the distribution, we can then use the softwares to find the area under the curve, or we can just simply use a lookup table for the p-value. I don't know if this makes sense to you. It's very important that you understand how the p-values are used. So there are two quantities that we are interested in. One is for a given p-value, what is the area under the curve? The other one is for a given sample statistic, what is the error that we are making, and how does that compare to the p-value? So the p-value tells us exactly where the cutoff is. or at least the quantity that we should use for the cutoff. Then I also said I will talk a few words about the one sample t-test, as it is often the one that is being used when in many practical setups. So for the t-test, which we say we distinguish the t-test as a distribution that has a certain behavior, and the mean behavior here being the fact that we may not know or we do not know the population standard deviation. Then how do we determine whether the mean of our single sample is significantly different from a known or hypothesized population mean? Our hypothesis is building on the relationship or a claim about the population. But in practice, we only have a sample of the population. And then we are asking ourselves whether the mean of that sample in some way can be the case for the population. In a very simplistic way, given the mean of the sample, is it the same mean for the population? To do that test, we then do the one sample t-test. We have a sample, we know the mean. Is it the same mean for the population? We cannot just conclude that the sample mean would be the same for the population. I gave you an example of how I could randomly choose travelers between two cities, and you would see how the answers might vary depending on my choice of travelers that I choose. Even if I choose from this class that you are in now, I will get a certain variation in your responses. How close is these variations to the actual case if I were able to get information from all travelers? That's the question we want to answer here. So we might also be, so the whole point is to compare the sample mean with the specific value when we are doing the t-test. An example of this could be also that we want to look at the average height of a sample, testing if the average height of a sample differs from, say, 170 centimeters. We want to test whether the average height of a sample differs from 170 centimeters. Maybe 170 centimeters is a claim that we are making about the population. And then we select a sample, and then we want to test whether that sample meet that requirement or not. And we call that, say, the null hypothesis, a claim about the population that we want to verify. If we say that in this class, the average student has a height of 170 centimeters, maybe we do not have enough time to measure the height of all the students, and then we simply take a certain small number of students and measure their height, and then we will get their average height. And then we want to know whether given this number, the claim that the average height of students is 170 centimeters, how likely is that claim to be true? By looking at the evidence of just a few students that we selected. So in that case, and because we do not know the standard deviation of the students in the class, we can use the one sample t-test. To do this, we also need to verify these conditions. As you've seen, the choices we are going to be making under any experimental setup for testing a hypothesis are often going to be governed by the conditions. You will always have to think about those conditions that the data or the sample or the population are put into in order for you to do the correct test. So for the one sample t-test, we require our data type to be continuous. Continuous values, as we've seen earlier, is those types of data that if you give me any 2 points, I can always find a point in between them. Height as an example, scores as an example, those are continuous values. That means that any value in between two values is a valid value. This is different from, say, discrete values. If our data was, say, about the number of students, and you give me two numbers, it is not immediate that any value in between those two numbers is also a valid number, because if you say 2 students and 3 students, and any number in between can be 2 plus 3 divided by 2, and that would be 2.5. But there cannot be such a thing as 2.5 students. Therefore, it is not a continuous distribution. It is a discrete. It only takes on specific values. In fact, the special mathematical name for such numbers is called integers, whole numbers, that we saw already in primary school. So for the t-test, our data should be continuous. We also require that the sample is randomly selected and representative. This is something that we also need to be able to comprehend. When we say randomly selected, means it doesn't matter which of the instances, which of the examples I pick from the population. I do not follow any procedure. I just pick anyone. In other words, one way of stating that is that every single example or every single point in the population has exactly the same chance of getting selected. There is no preference, there is no bias. Representative here means that if you pick a sample, the characteristics of the sample are the same as the characteristics of the population. For instance, if you have a class population, if our population is a class where you have male and you have female students, that is a characteristic of the population. A representative sample cannot simply be males or females. It has to be both. Then it's representative. So the sample is a randomly selected sample and it is representative of the population. I do think that in your research method course, you might have heard about representative sample. Sometimes you can hear the word stratification, stratifying, identifying that the strata, the traits, the characteristics in the sample are as the same as in the population. Then another very important condition that we've also seen is that we know or we don't know the standard deviation. For the case of the t-test, we do not know. And that's the whole point of using a t-test approximation. And the last condition is that the sample size is small. If the sample size is less than 30, if it's greater than 30, we can approximate that to a uniform distribution. If it's greater than 30, greater than or equal to 30, we can approximate that to a uniform distribution. And if it's less than, then we say the distribution is not uniform, and therefore the conditions for applying the Z distribution are not fulfilled. These are the opposite of what would happen if we were checking the conditions of the Z distribution. Because we cannot meet those conditions, we use the T distribution. An example could be to test whether the student scores differ from a national average. So a national average refers to the score for the students on a level of a country, for example, we may not have that data, and therefore we simply want to look at whether the statistic for our school in particular, in some sense, gives us reason to think that a claim about the national statistics is likely to be true or not. It can be the case that we also want to look at the average daily coffee consumption. I, I drink a lot of coffee. Of a group differs by a certain number of cups, 3 cups in this example. Either way, whether it is coffee, whether it is students, whether it is patients, the reasoning is the same. So having gone this course, it should not bother you what kind of population it is. It should bother you that you understand the statistics that you are looking into. Even though we are students that are doing education, in this case, I think as most of you are, the concepts and the ideas are the same for medical students. They can study populations of patients. The concept and the ideas are all the same. They will do exactly the same thing. But in this case, we maybe are more interested in educational related activities. The same concept, if these students were in a medical school, the concept would still be exactly the same. So it is important that you understand the concept, you understand the conditions under which those concepts should be applicable, because they are the same. It should not be any disturbance to you whether we are talking about coffee, whether we are talking about students' course, whether we are talking about patients. It is the same. You will also recall the formula for the statistics was very simple. We are looking at two things for the single or for the one population. On the one hand, you shouldn't be confused by these symbols, because the symbols are actually meant to represent different things, as you can see. In the case of the sample, we are looking at X to refer to the sample. For the population, we are looking at a different letter. In many textbooks, in many discussions, these two symbols are used. X to represent the mean. A bar means the mean of a sample X. The Greek letter mu is the mean for the population. And in the case where the sample is exactly behaving as the population, this difference would boil down to 0. And that's why I often say that this is how much error are we making? If we knew these two quantities, are they equal? If they are, it doesn't matter what the denominator is, because it would be a 0. But in many cases, they are not. And then we are asking the question, how close are they? How different are they? And to make this estimate correctly, we scale that using the size of the sample and the standard deviation of the sample. So this is the standard deviation of the sample divided by the square root of the number of examples we have in the sample. This is a scale factor. This number is constant. This number is constant. And then we divide this by this, and we get a measure of the t, a statistic. We call this the t statistic, and there is a corresponding value for the z statistic that we've seen. When we calculate this error, we can compare it to the critical value or the threshold value, which is something that we predetermine before we conduct our experiment. We say we want to have some level of significance. Is it a 5%? Is it a 99%? We're dealing with a 99% or a 95% or a 96%. that is where we know what the critical value should be, the alpha value that we're dealing with. And then we compare this, our statistic that we calculate from our sample and mean to the corresponding critical value and determine whether we are rejecting or admitting or keeping the null hypothesis. Keeping it does not necessarily means we are admitting it. It basically means we have no proof to reject it. Maybe at some point there might be a proof, but so far there is no reason to reject it. Since we cannot have both the null and the alternative hypothesis, we have no reason to dismiss the null hypothesis, and therefore we cannot keep the alternative. We have a good reason to dismiss the alternative, and therefore we only can uh, keep the alternative. We cannot keep both of them. And keeping it doesn't mean that it is 100% correct. It simply means we don't have enough evidence. So, and then the last thing I would talk about here, or the last bit, one thing is that the steps that you are used to perform either the t-test or even the z-test are almost always exact. I want you to know these steps because we will revisit these steps as we go further for the two population case. And you should know these steps offhand. You should learn and understand them. And the step says in the first, what is the statement for your null hypothesis? The statement is the claim. In a question, in a problem, in your thesis, you put down that statement in a way that will allow you to be able to do that test. Often you formulate that as something equals to something. The sample mean of a population in this case equals a certain value. That's a claim. The alternative, you should state the alternative as well. And the way you state the alternative, we were very strict on how this should be. If the null is an equal to, the alternative can either be not equal to, the alternative can either be greater than, it can either be less than. It is important that you think in those terms because it affects how you do your calculations later on. Then you have to either have a reason to say that, well, the problem statement requires me to use a certain level of significance, or you yourself doing that research, trying to do that experiment, have to make an assumption and say, okay, I will work with a significance level of 0.05, or in other words, I want to be able to check the significance level at the point of 0.05 or at 0.01. And conversely, it means you are looking at the confidence interval in this first example of 95%, in this second example of 99%. How close do you want to do your test? Either you have a reason because it is stated in the problem, or you make your own assumption and you work with that. And of course, you know that if you change that assumption, the result that follows might change as well. Then the next step is you're clear about this, and then the next step would be you verify the conditions, and then you use the formula that we just see. And then the next step is that you calculate, after calculating your statistics, you compare that with the critical value, and then you make a conclusion. These steps, read them, understand them. They are used over and over and over in the book. They are the same. Either you're dealing with a one population, one group, or you're dealing with more than one group. You often hear about the treatment. A certain group of patients receive a certain treatment, another group doesn't. In fact, this statistic is simple and basic, and as approximate as it sounds, is actually the basis whereby we decide whether a certain medication should work or not is actually a key to for international organizations to actually say, well, this paracetamol really do work. We should give it to people. The way they make that decision is based on the statistical evidence that they establish. If the statistical evidence support a certain claim that a certain drug is effective or not. So that's how strong these theoretical foundations are in real life. They affect you and I. They affect everybody. How should we give this COVID medicine to people? How do we know? Well, we conduct an experiment to see whether patients that received a certain drug, that's called experiment. Of course, experiments have their own risk. And I know that we have a lot of notions about this in Cameroon. And then we compare the group of patients who received the treatment to the group of patients who did not receive the treatment. And then we say, well, it does look like the results we are getting from the sample are not simply, we cannot reject, say, a null hypothesis. They are not simply coincidental. We we expect those results in the population. And in that case, we haven't given the medication to the population, but we expect that the population would have these kind of results. If they are good results, of course, we accept the medication. If they are bad results from the population, then we could still draw the conclusion whether those bad results would be expected in the population or not. If the statistics suggest that we are going to see something else in the population, maybe there's a reason to still give the medication. So this concept and this way of thinking is really very useful in our lives. So just a simple example before we actually move to the course material for today. Uh, a teacher wants to know, at least in your case, is a teacher wants to know if the average score of their class, the class in this case have 15 students, the sample size is different from the national average of 75%. So the claim is that the national average is 75%. If that is true, let's look at a small sample of this national. The sample here is just our class compared to the national. And then we'll realize that, well, our class have a mean of 78% and a standard deviation of 10. So how is it true then that the national average is 75? That's the basic statement we want to verify. Then we state that as a null hypothesis. Well, let's claim that the national average is 75. Then some other alternative is then that, well, the national average is not 75. That's what we want to claim. And to verify this, we then calculate our t and see that our t, because we're using t here since we do not know the national standard deviation, we get an approximate value for that. And since we are looking at a 75 or 95% confidence interval here, or we set our alpha to 0.05, we would then compare uh, with the critical value at that point for alpha equal to 0.05 with 14 degrees of freedom. Basically, we divide with the n minus 1 and the n is a 15 here. And if the calculated t value is greater than our critical value, we reject the null hypothesis. Um, good and fine with a single population, but as we will see, it's a very simple world where we simply have one population and we take sample from that population. What happened in practice is that we are not just studying one group. In the case of medication, in terms of, say, we are applying a method in a classroom, we often deal with more than one group. And that is the idea of two populations. In one group, we apply a certain method. In another group, we apply a different method. We are interested. How do we then do approximations when we have more than one group? How do we establish the inference in order to either we're comparing the two groups or we are trying to understand whether a certain thing or a certain technique or a certain behavior seen in one group can be approximated to the other. So how do we use the sample data to draw conclusions about the differences or the relationships between the populations of interest if we have more than one group? And this is a more practical case where you will always deal with more than one group. And would see that beside a very few set of conditions, or at least a few set of thinking about two groups, every other thing remains the same. And that was what I mean when I said from the beginning that you would see a pattern. Let's first of all look at what could be interesting in terms of what is new when we are dealing with two populations. So again, as in the case of a single population, the mean value of the two populations could be of interest. We are looking at, are these two populations behaving the same with respect to some characteristic that we are interested in? And therefore, we look at their mean values. We can either have the situations that we've seen before, which are that we know or we do not know the standard deviations of each of these populations. This information is going to be useful because if you're thinking about that pattern of calculations, it's the same. Do we know or we do not know the standard deviation for these two populations? Is not enough to know just one. If we do, it will influence the way we are going to compare these two groups or these two populations. We would test for comparing the proportions, not just the means, again, of the two populations. One important thing, which is new now, is whether there are matched samples or they are independent. Are these two populations or these two groups independent, or we are looking at matched samples? What do I mean by matched samples? Suppose you take a group of students and you ask them to do an exams, maybe just a crude example. You take the same group of students and you teach them a certain technique, and then you ask the same group of students to do another exams. You can realize that because you're dealing with the same group of students in the first case and the second case, you expect to have data about these two group of students in these two cases. So there is some kind of a correspondence or a match in those two. Suppose now you take one group of students and they do an exams. Then you take a second group of students, not the first, the second, and you teach them something, a technique, and then they do the exams. You do not have a match case because it's not the same group of students. Then it's a question of what is the differences or similarities between these two groups. So this would be whether they're independent or not. So we would, in addition to what we've discussed, be talking as whether we have a match sample or we have an independent sample. This will also affect how we do the statistics on two populations. Before we move on, what time is it now? Let's see. It's 6 o'clock, so we are aiming to have been finished at 6:30. My question to you is then, is it Saturday? Is it possible to finish at 7?
Yes, by my side.
Is that true for everyone? If it's not true, then I know that we are finishing in a short while, and then that means we still have a makeup to do.
So there's no problem. We can continue.
So we can continue and finish by 7. Okay, good. All right. And if you need a break, please let me know, because I know it's not easy to sit and listen. On the other hand, it's still morning. So we're talking about the case where you have two populations, and I'm saying that one additional piece of information to what we already know is either we know that these two groups are matching or they are, in some sense, independent. This will affect what we'll talk about further. The process is very similar. Again, that's why I was saying that you need to master that process. And the process is the same. Formulate your null hypothesis that assumes that there is no difference or a relationship between these two populations. The only difference now is that you are testing two populations. As either there's some difference in similarities of behavior or there's no difference. That would often be your null hypothesis. Your alternative is to contradict that statement. Maybe the null hypothesis says that there's a difference and the alternative says there's no difference. Those are your two hypotheses, your alpha and your null hypothesis. Then you will still encounter the same challenge. What kind of test should I use in order to determine whether it's the null or the alternative? And in order for you to do that, it will be based on assumptions and conditions about your data. As usual, or as before, in the case of a single population, you shall be calculating the p-value as a way to determine whether your evidence from the sample is good enough to reject or to not reject the null hypothesis. And given your level of significance, or given your assumed level of confidence, or your critical value, you would do a comparison again one more time with this critical value. And based on that, you can claim that, or you can conclude, not claim, that your null hypothesis stands still, or that you reject, depending on how far away your p-value is from that significance level. Now, you would see why I decided to take the pain of going through and recalling those other things here is that we are looking at the same pattern. The only difference in this case is the formula. We do not have just one population. And I have, as we mentioned at the start of this lecture, sometimes we can use subscripts to determine specific instances of a variable. If I take away 1 and 2 in all this formula, and I take away the subscript 1 and 2 and just have x here, and just have mu here, and just have sigma here, and just have n, it is exactly the same formula that we've seen before. So this is the distribution for the case of two populations. We are asking the difference in the samples means of the population, the difference in the sample means of in the population means, and their standard deviations of the two samples. It is a very logical expansion of what we've seen before. Just that we have the difference minus the difference. Instead of just having the x bar minus mu divided by theta, the square root of theta divided by n, we have x1 minus x2. Those are the mean values in two samples from two populations. Mu1 minus mu2, the mean values in the two populations, population 1 and population 2 in this case, and the square root of the standard deviation of population 1 divide, or the variance in population 1. When you square standard deviation, you have variance by n1. which is the number of samples in population 1, and also the variance in population 2 divided by the number of samples in population 2. Sum all of that and take the square root. And then you have your Z statistic for two populations, two populations. So to study the statistic, the mean, if we do not know, the standard deviation. If we do know, the standard deviation of our populations. And what did we say again about standard deviation of the populations? Do we say we often or we do not often know it? I just said a lot about that before. How do we often know the standard deviation of the population? It's a yes or no answer.
We said that we can know it and we cannot know it.
But that often we do not know it, right?
Often we don't know it, yes, sir.
Because we're dealing with a large population. So if we do, then Z is our answer. And if we don't, what statistics do we use?
The T.
The T. And so this is the case for the Z. And then the case for the T is basically that we replace that unknown population standard deviation by the sample S1 here instead of theta for the population. It's exactly the same, except that this one is from the sample because we are the ones who collected the sample. We can calculate the standard deviation of the sample. We can do it in many ways. It's a standard formula. If we're dealing with an Excel sheet, it's easier for us to calculate the standard deviation of one sample from one population and the standard deviation of another sample from another population and square it, then we get the variance. And we know the number of examples in each of these populations. So it should be easier for us to come up with this as well as this. So we want to use this to do the approximation. So the formula is just a logical expansion of the previous case for the single population, for the one population statistic. So we say something about the matched samples. For the match or the paired samples, the difference between the two paired observations are analyzed using a t-test. The t-test here again is that we do not know the standard deviation of the population. So the difference between the paired observations, what is the difference between the paired observations here? We simply are saying that suppose we have, in that example I gave you, a group of students that did something and then the same group of students that did something. We do have, for every value in the first group, we have the corresponding example in the second group. And therefore, instead of dealing with these two groups, their statistic, as in this example, what we should do different is this. For all the measurements, we should take their differences, which we can calculate because we're dealing, if it was this particular class that we have here, and we ask questions to them in one experiment or in one sample, this particular class that we have, those of you sitting here now, 10 of you, then we teach you something. We expect that it influences or it doesn't influence you. Our second population is still this class. The same student in the first population is the same student in the second population. Instead of dealing with these two groups or two populations, we will calculate the difference in the answers for every single student and calculate the statistic using those differences. That's the difference with the match samples. So the data itself is the differences between these two populations. It's not in this case where we want to look at the differences by the statistics of each individual population. We rather calculate the differences between each data point and do the statistics on this new data, which is made up of differences. So that's the difference with the matched samples. And by so doing, we account for the correlation between the pairs. So in this case, when we compare the proportions from two populations, the Z distribution is used under certain conditions. We will have the proportion of population 1 minus the proportion of population 2. So this was the case for the mean values. We look at the differences. The case for the proportions, we still calculate the proportions using this formula that we've seen before. So it gets a little more mathematical now, where you might easily miss the logic. But you remember, we were comparing population 1 multiplied by 1 minus population 1 is greater than or equal to 5. And then we're comparing that same fraction. We're comparing it with 5 either way in our previous case for the single population. The Z statistic here, in case of two populations, all I can say is that the formula is expanded, but you need to also see that this is a logical expansion of the first formula, except that we are dealing with two samples. So you can see here that we have P1, which is the proportion in our first population, P2, which is a proportion with a hat. So you then take the difference between P1 and P2. We also have P1 and P2 here without the hats. So the P without the hat is the pooled sample proportion, whereas the P with the hat are the sample proportions from each of the population. And then for the combined pooled, as they combine, the one from the differences is this one. So this one is from the individuals, this one is from the combined. And combined sample here is this sample which was obtained using those differences. And then we divide by the characteristics. Here is the one from sorry, I'm confusing you here. P1 and P2 are the samples with the hats. P1 and P2 without the hat refers to the population. Population 1 and population 2. The proportions, the differences between the proportions in population 1 and population 2, the differences between the samples drawn from population 1 and population 2. P1 is the proportion. So unlike the mean, we had the mean difference between the samples and the mean difference between the populations. Here we have the proportions between the samples and the proportions between the population. That shouldn't confuse us. So how close is the difference in samples to the difference in population? That's what we have here. If they are exact, this should be 0. Then it doesn't matter what we have here. If they are not, we are approximating how close. We want to use the Z statistic to determine, is this relationship significant? Is the difference in our sample approximately the same as the difference in our population? And to do that, we scale it. And to scale that, we will need to get a sample proportion from both populations, which is P. That's what we mean with the pooled sample proportion here. So if we get the proportion from both and calculate the proportion itself, 1 minus the proportion, and we know the number of samples in each of these two cases, we simply multiply this and take the square root. I hope that makes it clear. If you have a question, please, you can ask. Again, this refers to the sample and this refers to the population. Now things are getting a little bit hot, isn't it? Especially for if you get rattled by the formula. Now, these are the two calculations you can make for the mean, but also for the proportions in the case of two populations. We still need to determine whether what the conditions are, just like we did in the first case, in order for us to know what kind of formula we should use. Whether we use the z-test or we use the t-test is again determined by the set of conditions. So the choice of the appropriate test will depend on the type of data that we're using. Are we talking about comparing the means or the proportions, as we've seen, the different choice of the test that we want to conduct? If we're talking about the mean or the proportion, whether the population standard deviation is known, and one additional criteria is, are they match or independent samples? So to choose the right test, in addition to the cases that or the case of this one population, we will need to know whether our claim is in such a way that these two populations are independent or they somehow are a match. And by the match, we already say what that is. Now let's look at the match. So for the match samples, also known as paired samples, we design, this involves a design where the observations are linked or paired in some way, as I've already tried to explain with the example. This will come up when you start to do your thesis. You might do a before and an after measurement, basically on the same examples. So to measure the same individuals before and after a certain treatment or intervention. Different from that case, you might want to look at the case where you want to match on a specific characteristic, such as if you pair the individuals based on similarities in age, in gender, or other relevant factors, you would still have a match sample, because you would have the same group with certain characteristics in one, and then another group with certain characteristics. So you can either match a before and an after, or you can match based on characteristic. There are other types of pairings which could be just natural pairs, such as siblings or couples or other characteristics. When you are dealing with a match sample and calculating the differences in the pairs, you reduce the variability and the variability here being how do the differences vary across these two samples. You are controlling the individual differences, and then you are only dealing with the data that consists of those differences. So the match samples can reduce the variability within groups, and that gives you a much more insight into your statistics. So in some sense, we can say that it does increase the statistical power. And this increase then allows you to detect smaller differences between groups. All this means that, or in simpler terms, we can have a sensitive, the technique would be more sensitive. It will uncover very nuanced differences, very small differences between the groups when you calculate the variability in each, or when you calculate the variability by looking at the differences and then conducting a statistics on that. So instead of comparing the individual groups, you look at their differences. You can then do a t-test for paired samples to determine if the mean difference is significant or significantly different from zero. For instance, you might want to compare the blood pressure before and after a new medication. I already mentioned the fact that this is commonly used in medical science. Each individual's blood pressure is measured both before and after taking the medication. And then you create a pair of observations for each individual, and then your analysis will then your analysis would then focus on the differences within each pair to assess the medication's effectiveness. While these concepts might sound a bit more confusing, especially the match sample, at the minimum, my expectation is that you should be able to understand this on a conceptual level. If further you have to apply this in your thesis as an example, I know for the fact that for the exams, you definitely might have to answer questions about this, at least on a conceptual level, but I do not see that, I might be wrong, but I do not see that you would be asked to do calculations for the case of two populations, but you can be asked to answer questions about the meaning of concepts or the procedures of how you would think. But as I was trying to say in the beginning, if you will have to apply this in your thesis, obviously you would need to go back and read. And either way, you should read more in chapter 9 of this book, where you have more detailed examples. I know that in the last meeting we talked about examples. I also do know that I also do hope that when we have the opportunity to do a workshop, we would also try to do an example on this in such a way that we can again see how these calculations are done in practice. But it would be very useful if you, in the first instance, go through the chapter, look at the examples, and even the video demos. For those who haven't looked at the book yet, I think it's quite an interesting way of dealing with a book, because you do have examples and then you have videos showing you how those examples are conducted in Excel. So it's really very safe supporting material. Going further, there is one concept I have mentioned for this one population statistic. Now we are revisiting that concept. When we talk about p-values as some sort of error of approximation, the p-values and confidence intervals, you might think of it as, hopefully I'm not confusing you here, as the relationship between p-values and confidence intervals. You might think of it as the relationship between null hypothesis and alternative. They are in some sense complementary, because when we talk about confidence intervals, it's the opposite of talking about p-values and vice versa. So the confidence interval is then the interval within which the statistic occur. The range of plausible values for the true population parameter. When we're dealing with a sample, it's on the p-value side. When we're dealing with the population, it's the confidence interval. Given the sample values at this extreme end, how close are they to the population? How far away? Are they so far away that the information we are getting is not possible, or that the information we are getting suggests that the behavior of the population is not, that behavior of the population we are testing is not possible, or they suggest that it is possible to see that behavior. So for the confidence intervals, we are back into the middle in the population. As I said, I try to not take you too deep into confidence intervals, but still it's almost unavoidable, but it's important to have some idea how these two relationships are connected, or at least how they are related. The confidence interval and the p-values that we've been talking about so far. We would say that confidence intervals allows us to estimate a range of plausible values. What do we mean by plausible values? Expected possible reality of the true population. They allow us to estimate the range where we could have the potentially reasonable population parameters. They give us a range. It's very important that it's a range. It's very important that you understand the idea of a range. The interval to expect a certain behavior of the population is called a confidence interval. Crudely speaking, roughly speaking. For example, let's suppose the difference between two population means or proportions is the statistic we want to estimate. We've talked a lot about how do the calculations from the sample, which is like a small subset of the population, allows us to determine if those claims about the population can be true. Now, we are talking about the claims about the population itself, not the sample. So the difference between two population means, or proportions, the confidence interval is a range of possible values for the true parameter, for the true population parameter. When we said 0.05, I said 5% or 95% confidence interval. So the 95% confidence interval. What range will that occur in? 95% refers to the chance itself, but it has to be within a certain range. If you think of the graph and the axis, we're looking at in what range does that occur. So we will then take the value that we are thinking of determining whether it's the mean value or what, and then we would calculate that range. First, by looking at the left value and then looking at the right value. This formula here shows is two values because we have a plus and a minus. So if it is the mean minus the critical values times the standard error, think of the standard error here as either the Z or the T. If we take that P that we're calculating, multiply that by the critical value, and then we subtract that from the population mean that we were claiming, we have a small value. If we then add that to the population mean, we have a large value. From the small value to the large value, we have a confidence interval. So this is a range because it's a plus and a minus. This one is what we've been talking about. And then we say the critical value. Is it a 5% or 95%? So if we combine the statistic that we calculated with this, we can estimate a range for a mean or for a proportion. The population, the range for the population statistic is the confidence interval here. So the point can either be, as I said, the mean or the proportions. The critical value is determined by the Z or T statistic, and then the standard error, which is the measure of variability of the point estimate. So at least at this level, there's a lot of formulas involved, which I haven't shown you. Not that they're difficult to understand. It's just that I want to make it simple for you to understand without getting taken away by the mathematical formulations. Let's take the example of, this one is an example of if we are calculating the confidence interval for a 95% confidence interval for the difference between two population means where we do not know the population, where the standard deviation of the population is unknown, which is one of the conditions we've seen many times. So we are looking at the confidence intervals for the difference between two population means. So the difference between two population means population 1, the mean value, population 2, the mean value. What is the 95% confidence interval for that population? Basically, what is that interval where this difference would occur with, I don't want to say 95% chance. If we repeatedly do it 95% of the times, that difference will fall within, and I don't expect you now to understand this, but I'll still say it. Confidence interval does not necessarily mean that the chances is 95%. The interpretation is that if we do it 1 time, 2 times, 3 times, and what are we doing? We are taking a sample 1, sample 2 from these populations, calculating the mean. If we do that 100 times, in 95% of the 100 times, that difference will fall within this range. That is exactly what we're doing. It is not that the chances that the probability is of doing it 1 time is 95%. No, if we do it 100 times and look at the results, then within this interval, we should have 95% of the results within that interval. And then we take the t statistic value that we're calculating, multiply by alpha, divide by 2, and then we multiply by the standard error for the t statistic here, which is the factor that we're dividing by. Remember, we said that t was equal to the difference in population divided by all of this factor here. So to calculate the 95% interval, confidence interval, we use this kind of a formula. I do not think, and that's where I would probably have needed your other teacher to say it, I don't think they will ask you in the exams to calculate confidence intervals, but you can be asked to explain it, I think. In addition, you might want to calculate the confidence interval when you do your thesis. So almost getting to the end of this, the conditions for a two-population test, we've just mentioned them. Before we conduct a T or a Z test for two populations, we have certain conditions that need to be fulfilled. For the T tests, we do not know the standard deviation of the population. Then we want to know whether the two samples should be independent of each other. This was a mistake here with a bullet point and nothing there. Or the two samples are not independent. In the case where we want to conduct a two population test, we would like to have two independent samples. So the two samples should be independent of each other. What do we mean by the fact that they are independent of each other? The behavior, the characteristics in the first sample should not be influenced by the characteristics in the second sample. If this condition is true, then whatever information we are finding in one sample, we are trying to look at it whether there is, from the hypothesis point of view, a coincidence between these two populations or not. It can refer to a treatment. You have two samples completely independent, and then we're looking at whether the effectiveness of let's make it simple. One group is given treatment, the other is not. So these two groups are independent. Then we're looking at whether the behavior, the outcome after the treatment is a coincidence or is actually can be related to the fact that we gave that treatment. For us to verify this, we need to have the two samples independent. And Matilda, I can mute you. Let's see.
Sorry, sir.
It's okay.
Say it's like you have muted yourself. I'm no more getting you.
Yeah, I was trying to mute from another student and I muted myself. Sorry about that. So I was saying that for us to apply the two population test, it is important that the two samples are independent. And I was trying to explain the meaning of that. More to that, we want the samples to be random. So data should be collected through a random sample method, which we've also discussed about what it means. And they should be following an approximate normal distribution, approximate in the sense that we just check certain conditions. The populations should be approximately normally distributed or the size should be greater than 30. And we've seen this and talked about this at length. This is for the central limit theorem to hold true, which we already discussed earlier in a previous lecture. So once these conditions are verified, then we can go forward to decide what kind of test. For the Z test, if we know this population standard deviation, We do not strictly require that they are normally distributed, but we have to check that n is greater than 30. This symbol here was some problem with the formatting. It should be n greater than 30. And for the z-test, in the case of two populations and a large sample size, the sample size should be large enough such that n1 multiplied by p1 hat, which we saw that it was the proportion from the first sample, n1 multiplied by 1 minus p1 hat, as well as n2 multiplied by p2 and n2 multiplied by 1 minus p2, which is something we have seen for the single population where we are not just using this. Each one of these should be greater than or equal to 5. We saw this as a formula. So NP should be greater than 5 for the single subpopulation for one population, as well as N1 minus into 1 times P should be greater than or equal to 5. We've simply just added that for the sec when we have two populations. This should be greater than 5 at the same time when this is greater than 5. This should be greater than 5 at the same time when this is greater than 5. The subscripts here simply says that we are dealing with two populations. Unless we meet these conditions, we cannot use the Z statistic. If we do not meet these conditions, the sample is greater than 30, and these proportions multiplied by the number of samples, proportion for sample 1 subtracted from 1 multiplied by the number of sample is greater than or equal to 5, and the same applies for the second sample. If these two do not apply, then we have to use a different kind of statistic, non-parametric test. We've mentioned and haven't done it yet that we would try to do this using software because many of these calculations, as you can see, require some other mathematical verifications in terms of example for the p-values and so on. So we'll go back to that point at some point before the end of the course. And the time now is what? The time is 7 o'clock. So I would probably leave this part of the lecture for which is on the chi-square as well as ANOVA, so we can have a makeup because I think there's no reason to rush through it. We should rather schedule a class to go through it in such a way that you can understand that. So which means that somehow during the week we might require 1 hour or so to go through this. And I hope that should be okay, unless there's something. I would suggest a time in advance so we can complete this. With that said, there's no reason to make the video unnecessarily long. I will